Okay, so in this topic, the fluid sampling topic, we are going to discuss first, like why do we collect samples? So if you are going to collect samples from one of your fees, then that's the most important question that you should be answering. Like why do you need samples from particular well or from particular reservoir? And then we are going to discuss the definition, like what the representative samples versus non-representative samples. That's a common misconception in the industry. So we will try to answer some questions there. And then we will briefly touch upon the methods of collecting samples and what are the challenges. So for example, separator samples versus bottom hole samples versus the open hole formation testing. And then we will talk about this ECM method, equilibrium contact mixing that Matthias mentioned yesterday. And then we will look at this quality check of the surface samples, the separator samples, and then there will be an exercise related to it. How do you check the equilibrium of the separator samples? And then we will be doing this exercise on flash calculation that we haven't done now. So we will do that exercise, and that will be connected to this the equilibrium check of the separator samples. Okay, so yeah, why are we here? So here we are mainly talking about fluid sampling in conventional reservoirs, but if you have questions related to fluid sampling in unconventional reservoirs, we will also be very happy to answer those questions. So fluid sampling. So the most important reasons why we collect samples is the first one to develop PVT models. Of course, we would like to have PVT data measured on the fluid samples so that we can tune our PVT models and use them in for different applications. So the different PVT models, we have already gone through the introduction of those. So we have PVT correlations, we can try to tune those, and then black coil tables, and then the more sophisticated models are the equation of state models. The second important reason why we collect sample is to get help on the fluid initialization. And what do we mean by fluid initialization? It means that we would like to know the exact composition that exists in situ in the reservoir. So if it's a we would like to know what composition we should input in our reservoir models that should accurately representative of the in situ fluids, and that should give us the right in place volumes of the oil or the surface condensate and the surface soluble gas. Yeah, so determine the original reservoir fluids. We also like to know if, for example, in a reservoir, if the fluid compositions are varying, for example, versus with depth or spatially, areally. We also would like to know that information. So collecting samples that are in situ representative help in this fluid initialization. In conventional reservoirs, this producing GOR is a strong function of the average reservoir pressure. So I think Matthias already discussed this, that if we have unconventional reservoirs, then the producing GR is a strong function of the flowing bottom hole pressures. But in conventional reservoirs, when we have high permeabilities, then the producing GR is mainly a function of your average reservoir pressure and also the degree of undersaturation, meaning that if we already know, we have seen these PVT properties before. So if we have a single phase reservoir fluid and we are producing that fluid and only the single phase fluid is going into the wellbore, so we will be producing at constant GOR until we reach the saturation pressure in the reservoir. And also the conventional reservoirs, the permeability levels are very high. So usually we can produce without fracturing, and we can also use the open hole formation testing usually without any problems. So the general recommendations regarding sampling is that try to collect samples early in a well's lifetime at low drawdowns and stabilize GOR rate, so that the samples that you collect are more in situ representative, so that you can use them, for example, to define the in situ fluid compositions in your reservoir and get the right amount of hard place volumes. And we also recommend strongly that the following data be reported when you collect samples. So one is a separator GOR, and that's the most important thing, that you get the right separator GOR reported in your PVT reports when you are collecting surface samples. So when you're collecting the separator oil and separator gas samples collected at the separator, then the GOR that should be used for the recombination, and that we are gonna see in the next slides, and also when we'll talk about the compositions, that the GOR that should be used for the recombination has to be at separator condition. So it is the SCF, the standard cubic feet of the separator gas, divided by the volume of the separator oil at separator condition. So that's the separator barrels. Also, the separator conditions at this time of sampling should be reported, because that's important to quality check the separator samples. Field shrinkage factor used, so that's something we used in the exercise yesterday. What is the shrinkage factor? And also the flowing bottom hole pressure at the time of sampling. That's just to see if the flowing bottom hole pressure was less than the expected saturation pressure of the sample, and just to have an idea whether the sample can be an in situ representative or not. Initial reservoir pressure, time and date of sampling, production rates during sampling, that will give us the GOR, for example, and then dimensions of the sample container, total number and types of samples collected, the target information. Oh, yeah, so the target formation, sorry, the name of the formation from where the samples were collected. Yeah, so we have a question here. Yes, please.
Can you hear me?
Yeah.
So I was wondering, like, how many samples were used to give a promising PVT result usually?
Yeah, it depends on. So you mean like how many samples you need to develop a good PVT model?
Yeah, exactly.
Yeah. So I think it depends. Generally, like the more samples you have, the more robust is the PVT model that you are going to get. But it depends on how complex your fluid type is, for example, and what you are expecting. Like what will be your production strategy? For example, so like for example, if you have a very conventional low GOR black oil, and you are just gonna produce it, for example, with depletion or water injection, then usually, like even if you have one sample with some conventional PVT measurements like TCE, DLE separator test, that should be good enough to tune your PVT model. But like if you are planning to do gas injections, then you need more samples, because then you need to do more tests, for example, swelling test or the slim tube MMP measurements, etc. So like, for example, in unconventional reservoirs, we have, like, for example, Eagle Ford or Montney, where we have a very large span of reservoir fluids being produced. So we have the well stream compositions vary from from wet gas to, for example, low GOR black oils. So in that case, if you want to develop a very robust PVT model that describes all the compositions and all the PVT data accurately, we need a lot of samples, and we need PVT measurements on all those different compositions, so that we cover the entire composition, pressure, and temperature space for our PVT model development.
Great, thanks.
Yeah. Curtis, do you want to add something?
No, that's. I think that's fairly clear. It depends on the process that you're wanting to model with the equation of state, the range of pressure and temperature, and composition. So it's this range of pressure, temperature, composition. So if you're only doing reservoir simulation, it'll only be at reservoir temperature. Of course, you'll have the surface processing to get products. You'll need the separator and stock tank pressure and temperature. So you'll need temperatures from stock tank to reservoir. Whether it's depletion, like Bilal said, or gas injection, that really is going to reflect the spread and composition of the ZI that you're, basically flashing at whatever conditions, P and T. So that composition dependence of the K values needs to be hammered out in the equation of state development. And to do that, you need PVT with varying composition. So you'll need either a swelling test for gas injection or for a reservoir with compositional variation. That's gas cap in the top and oil in the bottom and varying GOR from top to bottom. You'll need multiple samples from top to bottom, and you'll need to get PVT data from each of those samples so that your equation of state is predicting not only that one oil at the bottom, but the intermediate oil, the oil at the gas oil contact, the richest gas condensate, and the leanest gas condensate. So this ZI, the composition variation, can come for various reasons. If it's a simple oil, like Bilal said, low GOR oil, water flooding, simple depletion, whatever, then the range of composition is very small. And you might get away with 1 or 2 PVT samples. I think what he answered is exactly correct.
Thanks, Curtis. We have another question, yeah?
Hello, yes. With respect to separator sampling, right, is it also required to collect the produced water sample? And will it have an influence on the...
Yeah, so yeah, actually when we develop like PVT models, for example, the equation of state models, usually we only care about the hydrocarbon phases. But yes, you are right. If you are collecting water samples, that can be helpful, for example, to describe the water PVT properties and the water PVT tables in your simulator, for example. And Curtis, he has been extensively working on this now, and maybe he has more comments here. Curtis?
Yeah, I mean, the water can be very important, of course. If it's in situ water, it can be because of the compressibility effect on, the material balance, the rate of pressure decline in the reservoir, getting the compressibility right. If it's water injection, getting the viscosity right. In gas reservoirs, the water might conceivably contain a lot of H2S, CO2, methane in solution. And as you get to low depletion states, very low pressures, then you start getting an increasing amount of these CO2, H2S, methane coming out of solution at lower pressures. So there's a lot of complexity to the water phase, in addition to the production problems with water, scale, etc. So you need water samples for many reasons. And yes, it would be highly recommended in any new discovery if you're taking MDT samples, open hole formation samples. The hydrocarbon sections, you're obliged also to take samples of the water zones in order to get the salinity, basically, and the composition of the water. Now, the equation of state is not usually, we don't have equation of state models that include like in reservoir simulation, the water, H2O as a component. You can do that on the processing side. That's fairly common. You have some modules in PVT Sim and HISIS, things, models like that who are doing surface processing. They actually have H2O and even the solids in the H2O as components. And the partitioning of the gas, the oil, and the water phases, the partitioning of components amongst the three phases can be predicted by a cubic equation of state quite accurately, the component partitioning. So yes, water can be important. Yes, water should be sampled, particularly early in a field development. And finally, the water can be treated as part of the equation of state calculations, but not at reservoir conditions, almost never at reservoir conditions, but certainly in surface processing.
Very good, Carlos. Are there any more questions?
Yes, one more thing. Yeah, thanks for the clarification on the water. Yeah, and the one more thing is actually regarding the solids present, right? Sometimes what I've read is the solid particles can act as a stabilizer for emulsions in case there is an emulsion forming tendency. In that case, how important or means to sample for the presence of solids in the reservoir or where it is there?
When you say solids, are you talking about salt solids?
No, the fines, the sand and the other fines, which are.
Okay. Yeah, this is not really, I don't know. I think it's I mean, emulsions are their own animal, and I don't know enough about it to talk about it intelligently. So, you know, there's a lot of complexities with emulsions. It's not really so much phase behavior as it is surface chemistry, I think. And so I don't know where even to direct you on the solid side of it. It's probably important. I just wasn't aware of it. So we'll look into that and get back with you.
Okay.
Yeah. Yeah. So are there any more questions? I think there is one more. And
Gerardo here.
Yeah.
Just one question. We noticed in some of the wells, in some deep gas wells, that we have to keep on circulating MEG or glycol, and sometimes, you know, operationally, it's not. We just can't disconnect the glycol or the MEG injection because we are afraid of the hydrates, right, during well testing. Is there any research done or paper done on the effect? Because I never get to an answer on that.
High pressure, high temperature hydrate modeling.
Yeah.
With MEG and as a I don't know what they call it. Yeah, basically to avoid the hydrates forming.
Yes.
Well, again, I don't know really the answer for that. There's a lot of work historically done on hydrates, but not at the conditions you're talking about. How the methods in Chapter 9 that are covered in Chapter 9 probably don't reach the pressures and temperatures you're talking about. I know that there's been a lot of work done in Norway related to higher pressure and temperature hydrates formation, modeling, and so that's something we'll also have to come back to you on. Now, my understanding is that PVT Sim has modeling capabilities for hydrates, and I think also there's another software, probably that would be a go-to software. It was my mind's failing me, but they were bought out maybe 5-6 years ago by big engineering company KBC. There's several softwares. I'm sure HISIS also has hydrate modeling capabilities. The question is whether those software have been tested against measured hydrate data at the conditions you're looking at. So we'll try to come back with you either with a reference or with a person or person's names you might contact on that. Yeah.
And on another topic, if you take a surface sample while you are circulating glycol on your system, and you contaminate your fluid with glycol or MEG at surface during sampling capture, is that a known problem to the lab later on?
Again, I don't know. I've not been asked to look at it. There are, again, probably a limited number of EOS-based software that will model both the hydrates and the MEG. In this case, you're looking at the effect of MEG on the gas-oil phase behavior through contamination. Solubility of MEG in, let's call it the hydrocarbon phase or phases. It's something I've only studied H2O directly and not these inhibitors like MEG. I think in the same effort to get you a reply by the end of the week that we'll share with everybody, I'll try to see whether somebody's talking about this one, the MEG effects on that high pHD, but also this MEG effect on the oil gas phase behavior.
Okay, thank you.
You know, Bilal, what we might do, I think John Radulowski, he's our in-house specialist on solid phase behavior, mainly wax and asphaltenes, but he's, I'm sure, familiar with what's going on in the world of hydrates and MEG. Yeah. So we'll touch base with him, maybe even bring him in for a short session on Friday. Could be an interesting topic to have him discuss for 30 minutes. So we'll get back with you for sure on both those issues.
Thank you.
Yeah. So very interesting questions, and hopefully we will be able to get some material on this and try to answer those questions by the end of the week. Now we jump to the next slide, and now we are gonna talk about Okay, there is another question from Hans. Yeah.
Just a comment on what regarding sampling. I'm not so familiar with the glycol, but I know when I'm just very familiar with sampling, and I know that if you're going offshore to do sampling on even water or gas or oil, we prefer to use water glycol as a back pressure medium. So I don't think this is a problem regarding to the sampling you are taking, since that's what we are recommended using as a back pressure.
Mm.
So you're saying you don't think MEG is affecting the vapor-liquid equilibrium of gas oil?
I don't think so, since we recommended to use MEG as a back pressure medium.
Yeah.
But I'm not 100% sure regarding the water sampling. For the oil and gas sampling has no effect.
Right.
But
okay.
For the water, I'm not 100% sure, but we're recommending to use that.
Yeah. Yeah. So yeah, it's definitely a topic we'll come back to visit. I think if there would have been a big effect of MEG on vapor-liquid equilibrium of the gas oil system, I would have at least heard about it. So I suspect you're right on that. The effect of the water solubility on gas oil vapor-liquid equilibrium, that I'm quite familiar with. There's an effect, but it, for the most part, can be ignored in terms of the effect on bubble point, dew point, and hydrocarbon liquid dropout, things like that. 99+% of the time, it won't. Taking the water out of the sample, taking the H2 out of the mixture when you do the PVT measurements and modeling, is not a problem. But even for high temperature, but you might get exceptions where you have high H2S, high CO2 content in a high pressure gas system. That might be a case where it would be the exception, because you get so much partitioning of those components into the water coming into the gas phase could have an effect. You know, there's always this 0.1 or 1% of the cases where it might have an effect.
Yeah, very good. Yeah, I guess there are no more questions here, so we can move to the topic. So now we are going to discuss the definitions. What do we mean by representative samples, and like why, like when should we care about collecting the samples, like whether it's a reservoir representative or not. So the way we define the reservoir representative sample is any uncontaminated fluid sample produced from a reservoir. And it can be any fluid. It doesn't necessarily to be the exact fluid composition or the fluid sample that you expect at the reservoir. You expect in the reservoir at the time zero of your, for example, of your production. So like if you are producing from a reservoir, and if you have depleted that reservoir quite a bit, for example, and the reservoir has gone, for example, below the saturation pressure, you have gas cap, you have a free gas phase, and the oil phase producing, and your GOR is completely different than what you were producing initially. And if you collect samples even at that time, those samples should be reservoir representative, because they are representative of the fluid that is present in your reservoir. And then there comes, Eric. Sorry.
Eric Jensen here. Can you define uncontaminated?
Uncontaminated?
It's not always so clear. I mean, is there
Yeah, so any uncontaminated, we mean here that the sample should not be contaminated with an oil-based mud.
Okay.
Because it can be contaminated, for example, with water, but you know that water can be separated easily from the samples, and then you can get a good hydrocarbon sample. But if it's contaminated with oil-based mud, then that mixes with your hydrocarbon phase, and then it's not possible to separate it, and then the compositions and those measurements are affected by the contamination. But we can like we will come back to that. Like you can, even if you have an oil-based mud contaminated sample, you can actually do the decontamination and calculate what is the hydrocarbon phase composition, the reservoir representative sample composition for that sample. But the problem is that when you are doing the PVT analysis, you cannot do the PVT analysis on your reservoir representative sample, because you don't have that sample. You can only do the mathematical decontamination and calculate the composition of that sample that you expect in the reservoir. Yes, Hans?
I'm not agree what you're saying here, that any uncontaminated sample is a representative, because you have a lot of things that can happen with the sample. You can have a large drawdown on the sample, and that will not be representative. So you cannot say that any uncontaminated fluid is a representative.
Yeah, so that's something that we are trying to make clear. Yeah, so we are trying to differentiate between a reservoir representative sample and an in situ representative sample. So the in situ representative sample is a sample that is representative of your original fluids in place. meaning that the fluid that you expect in the reservoir at time 0, that's your in situ representative sample. But reservoir representative sample is any sample that you produce at any time during the life cycle of your field, and it doesn't have any contamination with the oil-based mud. So that's why I said that it's not very clear to many people what is the differentiation between these two definitions, and that's what we are trying to communicate here. Yes, Curtis?
Yeah, so just the purpose of in situ representative samples, if you can collect them, is specifically and really dedicated to the operation of fluid initialization. It's like mapping in 3 dimensions your permeability, your porosity, your water saturation. You also have to initialize in 3 dimensions the composition or solution GOR. That's what we call fluid initialization. And to do that, you need to have as best possible estimates of in situ representative samples. Now, those samples need to be not contaminated by oil-based mud, A, and B, not altered from the in situ composition by multi-phase flow, like you're talking about, flowing below the dew point in a gas condensate, or likewise for an oil. So you basically have requirements. The one is that there's not oil-based mud contamination for in situ representative, and the second is that you don't alter the distribution of components that's actually found in situ that reach the sampler. Okay? And the purpose of those in situ representative samples is mainly to map out the initial fluid composition, or GOR. The reservoir representative sample, as Bilal is going to go into and discuss in detail, are samples that are produced by the reservoir, time 0, time 1, time 28, time 365, with whatever unit you like. Those are samples that are produced by the reservoir, and the equation of state is expected to describe those samples at that time, earlier, later, throughout the entire life of the well, so that the equation of state is required to describe the phase behavior, the volumetric behavior, the viscosities of all of those samples. And so those samples can and should be used to develop the equation of state, because your equation of state is expected to describe those samples. And even if it's day 1 and you've drawn the well really hard down, you know you're below the dew point, you know the GOR, CGR is not in situ representative, you're still obliged that the equation of state will describe all of the PVT phase behavior, dew point, the liquid dropout curve, everything of that sample that's not in situ representative, but is being produced by the well. And so any of those samples, they're the only requirement of a reservoir representative sample is that it doesn't have oil-based mud contamination. So those kind of samples can be collected day 1, day 10, day 365, or whenever. And they should all be used in developing this equation of state model, assuming that their PVT measurements are accurate. So this is not taught in textbooks. This is not taught in most PVT courses, but to us, it's very fundamental. Differentiation. We don't equate contamination with representativity. And we consider 2 specific types of representativity, the one for fluid initialization, the other for building the EOS model. So I don't know if that was clear, but that's, I think, what Bilal is going to go through and discuss now.
You have questions, so I guess maybe Eric?
No, I'm done. I think it was good now. Yeah.
Okay. Yeah.
Yeah, my question regarding contamination. Usually when we sample, it's contaminated. And do you have any kind of threshold where contaminated sample below or above that level can be used?
Yeah, so I guess if that's something, I don't know which paper Curtis can mention the paper, but what we have found that if you have any contamination, like any level of contamination, you can actually very accurately calculate the reservoir representative sample composition by doing the mathematical decontamination. But the PVT, like if you have only if you have collected samples and if you have only contaminated samples, then there is no other option but to measure the PVT data on those samples and then use your equation of state model to tune that PVT data and then just do the predictions of the uncontaminated samples PVT data, knowing the sample composition. Yes.
But when you say tuning, let's
Yes.
say you have a sample where the contamination is 50. Okay, you uncontaminate, you have the composition. That's okay. But
Yes.
when you tune your PVT experiments, that's all with the contaminated part. Then what are you tuning? You're tuning with the PVT experiment, which you know already that it's contaminated. So your model kind of questionable, right?
Yes.
So is there any work that says, okay, probably the contamination of the level of this we can accept, and above that, it's not usable or something like that? Do you have a kind of
a threshold?
Yeah.
Yeah. Curtis, do you know any kind of threshold? Does it exist or?
There's not any kind of definitive paper because that threshold would be different for a lean gas condensate, a near critical fluid, an oil. It would be different for each of those. So there's not, to my knowledge, a paper that gives some kind of definitive guidelines. What we basically say is the EOS modeling in a perfect world should only include samples that have no contamination with oil-based mud. Okay, that's in a perfect world. And open hole formation test samples with contamination oil-based mud can and should always be used to calculate the decontaminated composition for fluid initialization, whether it's 2%, 40%. You should decontaminate the composition and try to use that in your mapping of in situ fluids. Those are the two general guidelines that we operate with. And in most cases, you have relatively early in a field development production samples that are collected during production tests that have no oil-based mud contamination at all. And we take all of those samples, all of the PVT data from those samples that are quality checked and kind of quality checked and approved. We use all of those samples for developing the equation of state. And we don't use any of the samples that contain any level of contamination. However, then you get to this case of, like Gulf of Mexico, West Africa, high permeability discoveries where productivity is not an issue. They know when they start completing the wells, they'll make rates that are economic, without trying. Okay, so basically productivity is no longer an issue. In that case, many exploration delineation wells will not have a production testing program, and samples won't be collected. We won't have no samples are available except those that have oil-based contamination. There's a few of those cases that we've worked on so that the only samples we have to do the EOS model tuning on are contaminated samples, okay? So in that case, you have to, at least how we do it, we have a set of components in the equation of state that are describing only the oil-based mud components and in the right amount. So for one sample, it's 2%, another sample, it's 13%, another sample, it's 42%. So we have an equation of state that has a component slate of the in situ reservoir components and another component slate of only the oil-based mud. And then for each sample with PVT measurements, you assign the distribution of the oil-based mud components and do the modeling with that. When you're done modeling, getting all of the PVT measurements modeled accurately with this, call it hybrid equation of state, once that's done successfully, we simply take all of those samples we have that are contaminated, we throw away all of those oil-based mud components, we just remove them, and we make the calculations of those samples decontaminated to predict not laboratory measurements, but to predict the PVT behavior of uncontaminated reservoir samples, be it reservoir representative or in situ representative. So that you have to build the equation of state with oil-based mud contaminants in that case. You do that as best you can. The component slate and the properties of the components in the equation of state for the oil-based mud components need to be done according to whatever the oil-based mud consists of, and you do your best job. But if you have these samples that are production samples that have no oil-based mud contamination, those are the ideal samples and PVT data to develop your equation of state model with. So that's the long answer to a very an important question. But we just avoid using contaminated samples with PVT data unless we have to use them.
Yeah, so that's the kind of bottom line. Like if you only have these contaminated samples and you don't have any other choice, then you have to use those samples and the PVT data measured on those samples to come up with some kind of model that can give you the predictions of the PVT data of your reservoir representative or in situ representative samples. Okay, so I guess there are no more questions, so we can we can jump to the slides now. And that's something Curtis mentioned, that like these reservoir representative samples, and if we have PVT data measured on those samples, we would like our equation of state model to predict accurately all the PVT data for those samples. And the reason is because the accuracy of PVT data is not the same as the in situ representativity. So meaning that if you have good quality PVT data measured on reservoir representative samples, then you would like your equation of state model to accurately predict all that good quality PVT data measured on these samples here. And it doesn't necessarily mean that those samples should be in situ representative, because the in situ representative samples are only relevant for your fluid initialization. And if you have reservoir representative samples that are covering a good wide range of composition, temperature, and pressure space, your equation of state model should be robust enough that it can accurately predict the phase behavior of any composition that you might end up using in your reservoir model. So even though if like for example, if we take the examples of unconventional reservoir where it's almost impossible to collect any in situ representative samples, so there what you will do, you just use all your reservoir representative samples that are collected at different times during the life cycle of your field. You tune your equation of state model to all the different compositions and the pressure and the PVT data that you have measured on those compositions. And then you try to come up with the best estimates of your in situ representative sample composition to, for example, initialize your model. Yeah, so here so we will look at again try to differentiate between these two types of samples. So in situ representative samples, they represent the original fluids in the volume drained by the well during sampling. So meaning that what is the in situ fluid composition that you have at time zero in your reservoir. And this may vary as a function of depth. We already know that we may have compositions varying with depth. It can also vary from one fault block to another. It can be different for the different layers in the different reservoirs. And and again, this in situ representative samples, they may be difficult to measure directly, because we may have these neural bore multiphase behavior effects, and especially if we have low permeability reservoirs where we know that the drawdown is usually very high, or if we have saturated reservoirs or slightly undersaturated reservoirs where we know that the sampling the pressures can reach to can go below the saturation pressure, and we might end up getting two phases flowing into the wellbore. So in those cases, it's not possible to get an in situ representative samples, and the only samples that you collect are reservoir representative samples. Yeah, and that's something we have already gone through, that accurate in situ representative samples are used to determine the initial hydrocarbons, oil and gas in place. Yeah, so on the other hand, the reservoir representative samples, they represent any fluid produced from the reservoir at any given time of your field, and they are easily obtained. So you can collect samples at any point in time in your in the life of the reservoir. And then that's something and this is a very important point here, that these reservoir representative samples, they can be used to create estimates of your in situ representative fluids. And that's the main concept behind this equilibrium contact mixing topic that we are going to discuss, and Matthias briefly talked about it yesterday. So we will see, like, even if you have collected samples at some point in time where the producing well stream composition is not the in situ representative composition, but still with that sample you are able to accurately estimate what's the in situ fluid composition in your reservoir, and you can use those composition to initialize your model. Yeah. So, and this is another thing, that other important point that Curtis mentioned in the previous slide, that all the reservoir representative samples, if you have reliable PVT data, meaning that if you have good quality PVT data measured on those samples, and if you have good quality compositions, those are not contaminated, for example, with oil-based mud, then those should be used to develop an equation of state model. And all the samples, like, doesn't matter if the sample is in situ representative or not. Those samples and their associated PVT data should be used to develop a very robust equation of state model. Yeah, so now we are jumping into the different types of sampling. So there are three types mainly. So the first one is a separator sample on the left, and we already know, like, separator samples, we collect those samples at surface, and we can do the separator sampling for any type of reservoir fluid, so like gas condensate, volatile oil, black oil, and these are relatively cheap depending on how easily the setup is available near the well. And then we have bottom hole sampling. So this is just the introductory slide on the different types of sampling, and then we will go into a bit more detail on these different types. We have bottom hole sampling. So there you instead of collecting samples at surface, you collect samples at downhole. And this is usually recommended for the reservoir oils and not for the gas condensates. And the main reasons why it's not generally recommended for gas condensates is because the gas condensate reservoirs are usually near saturated. And also, like if you are 100% sure that if the gas condensate reservoirs are highly undersaturated and the well stream composition, it when it flows to this downhole sampler, it will remain in single phase until it reaches to the downhole sampler. Then you can use the bottom hole sample, but that's often not the case. And when by the time the composition, the reservoir in situ composition, when it reaches the downhole sampler, you already have some condensation happen in the wellbore, and then you might have lost some of the condensates because the condensate is heavy and it starts dropping out into the wellbore. So you might have lost some condensate, and the sample that you will be leaner in condensate compared to what actually was there. So yeah. The open hole formation testing, again, this can be done for any reservoir fluid type, and it's very useful for the fluid initialization purposes because you collect samples at pinpoint specific depth. And for example, if you have compositional variation with depth, you can actually determine those compositions variation with depth because you are collecting samples at a specific depth. And yeah, so that's very useful in that sense. So now we will talk about the separator sampling. So in the separator sampling, we collect separator gas samples. So there can be 20 liters of container. We may collect duplicate samples, and then the quality check is usually the opening pressure. So we check whether there is any leakage in the gas sample container or not by checking the opening pressure, and it should be very similar to the pressure at the time of sampling when the sample container was closed. Then we have the separator oil compositions. Yeah, so we also collect the separator oil samples, so that you can see here. So we have a bottle for the gas sample and a bottle for oil sample. And the composition of the oil sample, it's measured through flash GC compositional measurement. And that's something we will discuss on the next, not the next topic, but the next topic, that's the composition. So we will go through into more details of what is flash GC compositional measurement. And it's simply like the PVT lab, they take the separator oil sample and they flash it to the atmospheric condition and then measure the composition of its product, which is the flash oil and flash gas. And then then recombine them to get the estimate of the separator oil composition. So, but we will go through it in more detail when the topic will come. And generally now the PVT labs, they use this extended GC analysis. We get the C7 plus extended GC distribution, usually up to C30 plus or C36 plus the compositions. And also the molecular weight and specific gravity of the C7 plus fraction. That's kind of more important data because that will help us characterize the fluid, whether it's paraffinic or aromatic, and whether a single equation of state model should be should be used for all the fluids that are being produced from the field or not. So yeah, so that's also an important piece of information, and we will go through this in more detail at the end of the slide. The most important thing in the separator sampling is the recombination GOR, because you want to get it right. Otherwise, you will not be able to calculate the correct value stream composition. And the unit, so if the samples are collected at the separator conditions, for example, this is a separator gas collected and this is a separator oil collected, then you would like to know in what ratio they are being separated at the separator gas and the separator oil. So in that case, the unit of the recombination ratio used by the lab for the value stream composition calculation should be in standard cubic feet of the separator gas produced divided by the oil volume at the separator conditions. So that should be the separator barrel. And sometimes, like in the separator sampling, it may not be possible to, for example, like calculate the rate, for example, at the separator condition. So maybe you may be measuring the rate at stock tank condition. In that case, what you will be measuring at field will be the stock tank barrels of the oil, and you may be measuring the gas rate at the separator condition. So that will be the gas meter, but the oil rate might have been measured at the stock tank condition. But in that case, you would like to know what is the shrinkage of this separator oil to the stock tank condition. So that should be reported, and that's something we mentioned in the previous slides, that should be reported, what is the shrinkage of the separator oil to the stock tank condition, because that should be used to back calculate the separator oil volume from the stock tank oil volume. So that's something we also did as an exercise yesterday when we were correcting, or when we were multiplying the separator oil GOR with the shrinkage factor that we got from the report to convert it to the stock tank condition to calculate the total GOR. So that's the same procedure. You need to know the shrinkage factor to correct the stock tank oil volume to the separator oil volume to get the right recombination GOR that should be used to create the well stream composition. Yeah, so we also need to know the separator sampling conditions, the separator temperature and the pressure. And these are important to do this QC, the Hoffman plot, which is tells us whether the samples are in equilibrium or not. It's an indication of that. And also the bubble point of the separator oil at the separator temperature has to be very similar to the separator pressure, because the oil and gas phases, if they are in equilibrium, then the separator pressure has to be the same as the bubble point of the oil, and it should be the same as the dew point of the gas. Okay, so now we jump to the next sampling type. That's the bottom hole sampling, and so the bottom hole sampling is usually recommended for undersaturated oils, and when we know that the flowing bottom hole pressure is higher than the saturation pressure. And when it's not recommended for gas condensates for the reasons discussed previously. Also foaming oils and highly viscous oils. In that case, you may have problems with the tool being operated correctly at downhole conditions. So that's why for gas condensates, for these foaming oils and highly viscous oil, it's not recommended. And for gas condensate, we almost always recommend to get the separator samples. And you can also do this open hole formation testing that also gives us the information about the compositions that are in situ representative, and that can be useful for fluid initialization, for example. So there are certain quality checks that are done on the bottom hole sampling. So you check, for example, bottom hole pressure, because that tells us whether the sample was in situ representative or not, or you might have a different phase being flowing into the wellbore. So if you have two phases flowing into the wellbore, and if you have already reached the saturation pressure while sampling, then your sample may not be representative, for example. Perforation interval, yeah. So these are the different things in terms of the quality check. Okay, so the open hole formation testing. So open hole formation testing, when it's recommended, it's recommended for any reservoir, any reservoir fluid type, for example, oil reservoir, gas condensate reservoirs. And usually, like if you have layered reservoirs with different fluids, and you expect like different fluids exist in the different layers of your reservoir, then usually you try to do the open hole formation testing to get better estimates of the in situ fluid composition in the different layers. Because if you will try to produce them with the bottom hole formation testing, and if you have not isolated those layers, then the composition that you will get in the bottom hole sampler, it will be an permeability weighted average of the two layers, the total composition that you will get, and then you will not be able to do the proper fluid initialization for those two layers, for example. And same goes with the separator samples. And also like compositional grading reservoirs, yeah, it's very important to get open hole formation testing so that you get to know better how the decompositions are varying with depth in the reservoir. Yeah, so again, like if you have low permeability reservoirs, it's very difficult to get the open hole formation testing. But now I think with there are tools that are available, like Schlumberger has developed tools that can work in low permeability reservoir. But certainly if the permeability levels are very low, for example, in unconventionals, it's almost impossible to do the open hole formation testing. And then we should be careful about the oil-based mud, because we can have contamination, and then the samples may not be reservoir representative in that case. Yeah. Okay, so I think this is just the summary. So what are the advantages of surface sampling? We can collect samples directly, the desired sample directly from the formation we need, and then maintain full pressure of the samples. There is no, you can avoid using these surface separators. No surface metering is needed, because like in separator samples, one of the issues that you have the uncertainty in the gas rate and the oil rate measurement. So no matter how hard you try, there is always some uncertainty in the gas rate measurement and the oil rate measurement that uncertainty in the recombination GOR, and that gives slightly different well stream composition than what is actually there. And also yeah, so that's you also avoid the recombination errors, because you collect the total fluid directly downhole, and there is less sampling information transmitted to the PVT laboratory. So you don't need to tell like what recombination GOR the lab should use, for example, what are the sampling, like what were the sampling, the separator pressure and temperature. You don't need to know whether the samples were in equilibrium or not. So yeah, so there are some advantages of the subsurface sampling. And then the OFT samples, the most obvious advantage is that you collect samples a very narrow depth interval, and then those samples are representative of the flue of the formation. And those are in situ representative, so that you can use them for the fluid initialization purposes. The separator samples advantage is you collect a large volumes of samples, and you can collect as many as you want, and it's very easy, convenient, and usually less expensive compared to the surface sampling and open hole formation testing samples. You don't need to run any tools into the wellbore, and it's not a requirement that you should flow a single phase fluid, because then because the fluid is eventually separating into two phases, separator oil and separator gas, and then you use them to reconstruct the well stream composition. So I think we can take a break here, because it has been 1.5 hours now. If there are any questions, maybe we can take those first, and then we can take a short break before start the session again. Yes.
Yes, for the separator sampling, right? If there are say 3-stage separation in a topsides processing facility, so we need to take samples in all the 3 stages, right? Because actually we saw 1 stage plus the flash tank, the shrinkage correction for the flash tank condition. So if there are multi-stage separation, is it recommended to have sampling at all the stages?
If I have understood your question correctly, so you have a multi-stage separator sample. You have multi-stage separators, and so you have a first stage separator where you have and from the first stage separator, the oil from the first stage separator goes into the second stage, and from the second stage, the oil goes into the third stage. That's right?
Yes. Yes.
So yeah, so in that case, I think you only need to take samples from the first stage separator. So that's you only need to take sample, for example, from the gas phase from the first stage separator, and the oil phase from the first stage separator, and you need to know the GOR, the producing GOR, at that first stage separator, meaning that the volume of the gas being produced at the first stage separator and the volume of oil flowing through the first stage separator. And because those volumes will give you the recombination GOR, and you use that recombination GOR and the decompositions of the separator gas and separator oil to get the well stream that's going into the first stage separator.
Yeah, and the shrinkage that you're looking for will be measured by the laboratory.
Yes. But if you have measured directly the separator GOR, if you have measured the GOR directly at the separator condition in separator barrels, then you don't need the shrinkage, right, Curtis?
No, but they may want that. They may be using empirical correlations of that shrinkage, and not just shrinkage from separator conditions to stock tank, but through the actual remaining stages.
Yeah.
So you could just have the laboratory do the remaining separation stages at laboratory conditions and get that shrinkage factor. It's better and more accurate and more efficient than trying to collect samples at each stage in the actual process, I think.
Okay, thanks.
Yes, Gerardo.
Yeah. Have you come to have you come across the QC of the separator samples by using this isokinetic wellhead sampling?
Yeah, that's there's an SBE paper 28829. I think we provided.
Yeah, the institute composition. Yeah.
Yeah, and in that original paper, that there's quite a bit of discussion about that. What they used to call Thornton wellhead isokinetic sampling. It was developed at Shell, redeveloped at Shell, and commercialized, and then I think they sold the commercial methodology to a Norwegian company. I'm not sure they still exist.
Expro offers it, yeah.
Yeah, Expro bought, I think, the Norwegian company. So the history of it, and yeah, we have seen it used. The original Hoffman-Crump-Holcott paper, if you go back to that, we also provide that in the course materials, which is kind of this famous QC of separator sample compositions. That Hoffman paper actually shows a truck-mounted wellhead isokinetic sampling system. So it was being used and it was developed commercially back in 1950, whatever it was, the paper. So it's not new technology. And this SB paper 28829 that we wrote refers to all of that old technology of the wellhead isokinetic sampling that was being used back in the 50s. That disappeared completely until the Shell-Thornton methodology kind of reinvented it or started reusing it. And my understanding why they did that was because of the troll field. Okay. The troll field was this 40 TCF, 45 TCF gas, ended up being a gas cap on top of 6 billion barrels of an oil rim. And they were trying to get the gas samples. It was a very lean gas condensate because it was very low pressure reservoir, 2,200 pounds, I think. And the gas was essentially a dry gas, but the small amount of liquids was going to be very important for designing pipelines. I mean, it's such a big field. They wanted to get the detailed small amounts of these heavier components in the reservoir gas that they would be producing and transporting and processing, okay? So they tried to do sampling of these early troll field gas well tests using the Thornton isokinetic sampling. When I saw that being done in the early 80s, that's when this idea of the equilibrium contact mixing method kind of arose, and I started looking at it around 1984. And the idea was that and in that paper, 28829, we actually take a troll example, and we show that if you take the troll gas, knowing all the significant digits of all the heavy components, you know, from an equation of state, and you bring it to the surface and you lose all of the liquids in the separator. There's not very many liquids, but you lose them all. In other words, you only take the separator gas composition by itself. Where the wellhead isokinetic was trying to collect these very small amounts of these heavy components. So what we did was an example where we said, we'll take only the separator gas. We have none of those liquids. If you equilibrated that with, and they got 6 billion barrels of oil below, with any oil sample below that you collect independently, put it in the PVT cell at GOC conditions. Then what you found, and we showed it in the paper, is that you pick up all these small amounts in exact the right proportion into that reservoir gas in the PVT cell. So you basically, if you have a saturated gas oil system, that is a much more accurate and efficient way of getting the correct reservoir equilibrium gas composition, but it really only works if you have a saturated GOC.
Yeah.
So, okay, so if you don't have that, if you have an undersaturated gas, lean gas, and you need to use, and you really want to get small amounts of whatever heavies there are, then you can revert to trying to use either wellhead isokinetic sampling or separator sampling with isokinetic correction methods. So, but it's only in the absence of having an equilibrium oil where the ECM method is a better approach.
Okay.
But that paper and that discusses the wellhead isokinetic sampling and basically what Expro is providing is the same thing that was back in the 1950s. And it's a difficult, you know, thing to do right.
Yeah.
So you can do it, but there's some uncertainty clearly in doing it. So
Okay. No, thank you so much for the detailed answer. Yeah, that's great. Thanks.
Okay, so the next topic on the agenda is Watson characterization factor, and we are discussing this topic under fluid sampling, and you will see the reason why this topic, because with the name like Watson characterization factor, this topic looks a bit different than the topics that should be covered in the fluid sampling. But we will see why it's included in the fluid sampling chapter. How can I remove this here? Okay, that's fine. Yeah, so the Watson characterization factor, it's the expression for calculating Watson characterization factor is this. This is equation 5.35 in the SP monograph, and it's the Watson characterization factor. It's the function of the molecular weight and the density. And generally, when the PVT labs, they do the compositional measurements, they measure the average molecular weight and the density of the flashed oil or the surface oil. And this Watson characterization factor, it can help us differentiate whether our fluid type is relatively aromatic or paraffinic or naphthenic. And that's very good information for us when we are, for example, developing equation of state models. So for when we calculate with the help of measured molecular weight and density, when we calculate the Watson characterization factor, the Kw, if it varies roughly from the Kw usually varies roughly from 8.5 to 13.5 value, and if it's between 12.5 to 13.5, generally the fluid type is very paraffinic. It's naphthenic if the Kw range is from 11 to 12.5, and then 8.5 to 11, that's very aromatic. So yeah. So now on the next slide, we see like if you plot specific gravity molecular weight for the different components, we know that it has to be monotonically increasing function, because as the molecular weight increases, the density the density of the component also increases. And then these are the lines that represents a constant Watson characterization factor value. So for example, this gray line represents a Kw of 10. Then we have an 11, this is 12, and that's 13. And downwards, we have an increasing paraffinicity, meaning that if the Kw is higher, you have more paraffinic fluid. If it's lower, you have a more aromatic fluid. So here we have the ranges for the different fluids. Why that's usually important, for example, when for in terms of the sampling, for example. So usually when you plot the specific gravity versus molecular weight, and if you have different samples collected from the field, usually they should be closely correlated. So like if you are increasing the molecular weight, the specific gravity, we know that it should be monotonically increasing. And then if you have a if we have a constant Watson characterization factor value, and then all the samples should lie on the same line, on the same Watson or very similar Watson characterization factor value. But what we see here, so here we have a bunch of samples. Each point actually represents one sample measurement. So average molecular weight and density measured on one sample on the field. And so the samples that are the markers that are filled with the black color, those represents the bottom hole samples. So those are the average molecular weight and density measurements from the bottom hole samples. And then we have these open circles represents the average molecular weight and density measurements from the separator samples. And what you see that and these all measurements are from the same field. And what you see that the bottom hole samples they tend to be more slightly more aromatic, have slightly higher Watson characterization factor value compared to all these separator samples that we have collected and have done the measurement on. And the reason why the separator samples are showing a different trend or the value of Watson characterization factor, and it is a lot, we have a large scatter, is because all these measurements are affected by the wax accumulation. Because when you collect samples at the surface, at surface you have low temperature at the separator, and the samples that you are collecting may have too much wax or too little wax, and and the density and molecular weight measurements on the flashed oil from those separator samples can be affected by those wax. So when you're doing the density measurement, if you have collected too much wax, it means you will be getting lower measurement on the density, because wax components are usually very paraffinic and they have lower density, so you get a lower density measurement. And these bottom hole samples, so that's why, like, if you have waxy crude, the bottom hole samples are usually recommended, because then you collect samples at high temperatures and then you don't have these wax issues. And that's why these measurements from the bottom hole samples are more consistent compared to the measurements from the separator samples. Yes, Alexander.
I just have a question regarding that. But if your temperature of the separator is above the wax appearance temperature, then you should not expect dark scattering, isn't it?
Yeah, that's true. So if your temperature as a separator is higher than the wax appearance temperature, then you may not probably get any wax while collecting. But then you also have to be careful when you are doing the flash of that separator liquid in the laboratory, that you should, because usually as a standard procedure, when PVT labs, they do the single stage flash of the separator oil, they do it at ambient conditions. So that's 15 degrees C and 14.7 psia. And that temperature is usually lower than the wax appearance temperature. So if you know that you have wax issues, and even though you have collected separator samples at temperatures higher than the wax appearance temperature, you should communicate to the lab that this is the expected wax appearance temperature, and when they do the flash, the flash temperature has to be higher than the wax appearance temperature, so that you don't get any wax in the flashed oil. And when you do the density measurement, those should not be affected by the wax.
I think a general comment. It's a very good question, and it leads to some. I think if you have an oil, typically an oil, it could be condensate, but if you have a wax forming system, in other words, the wax appearance temperature is likely to lead to some wax formation in some samples, maybe in the laboratory. It's I think the consequence will be that this relationship between specific gravity of the flashed oil and the molecular weight of flashed oil will show scatter. In varying degrees of scatter, like you say, maybe in some cases you collect samples at temperatures above the wax appearance temperature, there's no problem. Other cases, it's a colder time of the year. You collect the samples, cooling happens. Could be a laboratory artifact. The point is that if you're a big scatter and kind of a consistent scatter shown like this is suggesting that there's probably wax forming, not randomly, but in different amounts. And and giving different, basically not reflecting the correct flashed oil, but basically. So I think a big scatter in this and a scatter in a certain direction will indicate that you have a wax related issue, and that maybe bottom hole samples, if again they correlate like they do here, where they seem to not be affected by the same scatter, it's a suggestion that collecting separator samples is a problem with respect to wax. You probably can't avoid it completely. It's just a red flag to be careful with.
Okay, very good, Chris. Gulnar?
Yeah, you've shown us the characterization factors. You've shown the Watson, and here is the radar.
Yeah.
Which one is preferable, or?
Yeah, so that's a very good question. So here on this slide, you see that it's FC, and FC. So it's another. So Watson characterization, it's one correlation that you can use to develop the specific gravity molecular weight relationship for a given field. FC, that represents the characterization factor from the Sureda correlation here, and we generally use Sureda correlation because that's available in the software that we use, FaceCom. But I guess you can use any correlation as far as it is following the trend, the measured trend that you have from the field. So you just try different correlation and see which one gives you the trend that you see in your field.
Yeah, thank you.
Okay, yes, Hans? Yes, Hans, do you have a question?
I had to unmute. Since I'm working at the PVT lab at Equinor lab in Bergen, normally all laboratories do the analysis at reported separator temperature. We have some separator temperature that is as low as 12 degrees. That's probably below the wax appearance, but before we transfer it to the cell, we always heat the sample up to 60-70 degrees to be sure that if there is any wax participation in the bottle, we get that into the PVT cell, and then we lower the temperature because we should do the analysis at the separator temperature, and then we can observe if there is any wax, and then we can report it.
Yeah, I think that's a good practice, but I think a little bit the problem is still that in the field, we actually see, and this is one of the cases we've seen it, that it appears that the sampling, in other words, there's wax precipitation going on in the field, in the separator. And when you collect the sample at the separator, you're getting excess, in this case, excess wax. In other words, it's sucking in extra wax that shouldn't be in that sample. You might also have a situation where you've lost some wax and you're sampling a sample with too little wax. So it could go either way. The point is that if that wax excess or wax loss is occurring in connection with the sampling itself, then it wouldn't really help homogenizing with temperature in the lab. You see what I'm saying? If the sample bottle is not the cause of the excess or the too little wax, in other words, if what goes into the sample bottle has too little or too much wax in it, then it doesn't help homogenizing that incorrect separator oil.
Yeah.
So just to keep that in mind. That's what we believe actually happened in this. This was in Southeast Asia, and they were aware it was waxy, and they were doing, I think, a lot of similar things to what you were doing as well here, heating the sample, homogenizing. But then you still saw this very clear, what appears to be excess wax that's being collected. in the separator sample. So.
Yeah. Very good. Hans, just a follow-up question to you on this. So when you heat those containers, so do you only heat the separator oil sample container, or do you also heat the separator gas container?
No, we normally I also heat the gas sample to about 60-70 degrees. Even the separator temperature is 12.
Yeah, because the one problem you may end up getting with by heating the separator gas sample is that if you, for example, if there is some kind of liquid carryover with the gas, and that gas sample that you have collected, it will be in equilibrium. At 12 degrees C, at the separator temperature, you will have two phases in your bottle. In the gas bottle, you will have a carryover liquid and an equilibrium separator gas. That should be the right separator gas. But if you will heat that container up, then some of the carryover liquid will vaporize into the gas phase, and then when you will do the measurement of the separator gas, the composition, that will not be representative of the true separator gas you have.
Yeah, you're right there. But we also check for a carryover at room temperature.
Okay.
You can just open the bottle. You can set it up in horizontal position, and then you can check at the bottom if there's any carryover at all. And if you have a lot of carryover, okay, you have to take care of that.
Yeah. That's good. Just wanted to make that comment. Very good. So I guess we just jump to the next slide then. Yeah. Okay. So now this next thing is an exercise, and what we are gonna do, we are gonna calculate the Watson characterization factor for the oil PVT report that we have. So for the oil sample and the gas condensate sample, and try to guess whether the fluid type is aromatic, naphthenic, or paraffinic. So that's an exercise we are gonna do, and I think this exercise on the flash calculation is also due, and that we are also supposed to do that exercise, and as I said earlier, that we will do the splash calculation exercise after finishing the fluid sampling topic. So I will just go through a small topic just to introduce you guys on this on the equilibrium check of the separator samples. There are a few slides on that. We just go through those slides, and then we do this exercise on the flash calculation. We do the exercise on the QC of the separator samples, and we also do the exercise on this Watson characterization factor calculation. And after that, we will finish the rest of the topics in the fluid sampling. Okay, so yeah, so I will just show these slides here. The quality check of the separator samples. Oil samples, when we collect the separator oil samples, we generally do the quality check by checking for any leakage by measuring the bubble point pressure at separator temperature, because we know that the bubble point pressure at separator temperature has to be very close to the separator pressure at the time of sampling. And also, yeah, if the measured bubble point is 1 to 2% of the separator pressure of the oil is considered valid. That's, I think, from this this range, 1 to 2% is actually from this document of API recommended practice of sampling. Yeah, and for the gas samples, we generally check again for any leakage. So we check whether the opening pressure is close to the separator pressure at the separator temperature. And if the opening temperature is different than the separator temperature, then you can calculate the opening pressure that we should expect from the in the container from this equation, which is simply this the ideal volume gas law. So P1 V1 upon T1 is equal to P2 V2 upon T2. Considering we haven't there was no leakage, so the number of moles are the same at the separator condition and the lab conditions. And then there's one check that we do is the equilibrium check, and there we try to see if the separator oil sample and gas samples they were in equilibrium at the time of sampling. And for that purpose, we use this Hoffman plot or the KPF plot that we are gonna do the exercise on. And what that plot shows us actually, so if we plot, that's something we plotted yesterday during the exercise, that if you plot log of KIP versus FI, then generally it's a straight line. And the data, if we have the lab data, then the measured compositions of XI and YI, the superior gas and superior oil, and they should follow the straight line, for example, from standing correlation. So the standing correlation gives the slope and intercept, which we calculated yesterday, which were A0 and A1. We will see it one more time during the exercise. So a standing correlation gives the approximate slope of this straight line, and the lab data should fall closely on that straight line from the standing correlation if the data is in equilibrium. So that's something we are gonna do in the exercise. So this method is the Hoffman et al. Method, and these are the equations. So Hoffman, that's this paper, Hoffman and Crump, that Curtis was mentioning about when he was commenting on this isokinetic sampling. And what they have proposed in the method, that if the log of KIP should be a linear function of Fi, where A1 and A0 are the slopes and intercept. And we have found that these slopes and intercept at low pressures, like at separator conditions, are generally reasonable from the standing correlation. So that's why we use the standing correlation as an indication of what slope and intercept you should expect for any measured data. And Fi, like yesterday we calculated Fi from this. Yeah, so yesterday we calculated Fi as like this, 1 over TBI minus 1 over T. So that's the expression we used to calculate the Fi yesterday, and FBI values for the different components, they were from standing table that I showed yesterday. And then the boiling points were also from the standing table, and then T was the separator temperature. And so this is the same expression. So this whole term here, so if I take this this guy here, so this is actually this BI value here. And then the rest is the same, 1 over TBI minus 1 over T. So standing has given the values of BI for these lighter components which are mainly function of the boiling point, the critical temperature, critical pressure of each component, and that's the standard condition pressure. So yeah, and generally what we have seen that on this straight line, this C7 plus component, usually that falls off the straight line, and that's completely okay because this is just an average component and it is calculated from this average carbon number from standing correlation, which may or may not be very accurate correlation for the C7 plus component, but all other components, they should be very close to the straight line. Yeah. Very important question is that like if we, for example, if we have collected samples, separator oil and separator gas, and if we did do this kind of QC, and if we, for example, found that the samples were not in equilibrium, then should we use those samples for the recombination? And if we have any PVT data measured on the recombined sample using the non-equilibrium separator oil and separator gas, should we use that PVT data, for example, for equation of state model development? So anybody would like to pass their comments on this question? Like, what do you all think about it? Maybe we can take 1 or 2 comments, whoever wants to add comments here. What do you think about this? Like, if you have the non-equilibrium sample, should we use the PVT data from those samples? And what PVT data we should be using for EOS model development, for example? Okay, so I guess because we went through this the differentiation between the reservoir representative and in situ representative samples, right? And we know that any sample that you are collecting from the reservoir at any point in time, that is considered as a reservoir representative sample. And any PVT data measured on any reservoir representative sample should and always be used for EOS model development. So if we have good quality PVT data, for example, if we collected samples, separated oil, separated gas, they were not in equilibrium, we recombined those samples to calculate the well stream, and then we did, for example, CCE or CVD and DLE and separator test, and all those measurements that were done in the lab, all these experiments done in the lab, those were very good quality PVT data measured on the well stream composition. That on that well stream composition, then we should be using all that data for the EOS model development. The only data that we should not be using in that case for that particular sample is the separator oil and separator gas compositions and the K values that we are getting from those compositions, because we know that that data is not, because we know that the if we take that well stream composition given by the lab, and if we will flash it to the separator pressure and temperature reported by the lab, we should not be getting the same K values as reported or measured from those samples, because those K values is equilibrium ratios, right? So if you do the EOS model flash, then you will always get the K values of the 2 thermodynamic phases that are always in equilibrium. So the EOS calculated K values at separator conditions will always be different than the K values we have measured from these samples, which are not in equilibrium. But all other data, if we have measured any other data, well stream, the CCE, CVD, or DLE, or any other experiment, that should be used in the EOS model development, because we went through this point that the accuracy of PVT data is not the same as the reservoir, it's not the same as the representativity of the sample. So the well stream composition that you might have calculated from those non-equilibrium sample that may not represent the true well stream flowing at that particular time, but all the PVT data measured on that quote unquote wrong well stream, if that is accurate and you know that composition of the well stream used to measure that PVT data, you should use all that PVT data to tune your equation of state model. Yes, Gulnar, you have a question?
Yeah, so basically, if I understand correctly, we should not use a composition from the single flash, right? And try to combine it, because you can do the single flash, you have a separator gas and you have the separator oil, and then they do the flash, right? And then they try to recombine it. Is that what you mean?
I mean, I think you meant this the flashing of the well stream in the PVT lab, the single stage flash of the well stream in the PVT lab.
No, the separator sample. Here we're talking about separator sample, right?
Yes.
So in case we found that the Hoffman values were inconsistent,
yes,
which PVT experiment we should use to recombine mathematically? Or, I don't know, is it D-flip or a separator experiment?
Yeah, so what I'm trying to say that if you, yes, Karis, do you want to say something?
I think the question is a little bit, if the Hoffman plot indicates lack of equilibrium or lack of consistency, if that's the situation, what do we do with the samples? Is that a little bit, is that correct?
Yes, that's correct.
Okay. And so how to frame this? The one thing is to get a recombined composition, Wellstream composition, that you use in the laboratory to make PVT measurements, right? If that's the purpose, which it normally would be, that you say the separator, you're going to make a separator recombination in the lab, create a Wellstream composition, you're going to make PVT measurements on it, CCE, CVD, whatever it is, okay? So the most important thing, really the only important thing about the composition is that you know what's in the PVT cell. Okay? And so if you believe the laboratory measurements are correct, the composition of that separator gas and the composition of the separator oil are correct compositions, what's in each of the bottles, and you make a recombination with the test GOR, for example. So you think that that total Wellstream that physically you've recombined now is correct, okay? Then you can use that physically recombined sample to do your PVT measurements. Having the equilibrium of the separator gas and separator oil is not a requirement to get good PVT measurements for a known composition, okay? So the point is that if we feel like we know the composition, what they do in Norway quite a bit is that they'll actually take the physically recombined composition, a mixture, the physically recombined mixture, and do a single stage flash composition determination of that physically recombined mixture to check against the mathematically recombined composition. So you actually have two compositions, the one from the mathematical recombination of the separator samples and the one from the physical recombination that's then analyzed. Of course, if those two are consistent, then you feel comfortable, you know what's in the PVT cell. You can then take the PVT measurements and you can use that data in developing the equation of state. All right, so that's, if, however, for some reason you want to have what were the actual equilibrium compositions in the separator, okay? If that's the question, if for process calculations or for some other, just having K values in the EOS tuning of the separator, if getting the equilibrium compositions in the separator accurate is important, what I would recommend doing is just taking the separator gas and separator oil that don't show a good consistent plot like this, okay, that there's some deviation, you don't think it's completely in equilibrium, is just to take and take that recombined physical mixture, but bring it to separator conditions. In other words, you do the physical recombination and you just equilibrate it at separator conditions. You create your own separator in the laboratory and you get the compositions of that equilibrium gas and equilibrium oil at separator conditions. That will give you, should give you accurate separator gas, separator oil, known to be in equilibrium, right? K values. That separator gas, that separator oil created in the laboratory, when plotted on this plot, better show consistency, right? So that's a way, in a sense, to get equilibrium compositions from samples that are, for some reason, not in equilibrium, okay? Maybe they're collected in our time difference. You know, there could be a lot of reasons they're not in equilibrium. So that would be a way to get to find out what the known equilibrium composition should be, what should have been in those bottles if they were collected consistently at the same time. So it's a long answer, but you know, in the one case, you can just use the samples, do the physical recombination, make sure that mathematically recombined composition is consistent with like a redetermined composition, and then you know what's in the PVT cell. You can then use that to do the PVT modeling, EOS modeling. That's normally what we do. We go ahead and use the data. We use the laboratory PVT experiments. We use the calculated recombination composition, but we don't try to predict the equilibrium gas and oil compositions that were in the sample bottles because they weren't in equilibrium. So we don't use that data in the EOS tuning, the K values, so to speak, from the separator samples. Otherwise, we could use those separator K values. If things are consistent like this, you can actually use those separator K values in the EOS tuning together with the reservoir PVT data. Gunnar, was that, I mean...
Yeah, thanks.
I hope it wasn't too...
Thanks again, Curtis. I can just mention briefly about one case study that we did. So we were developing this basin-wide equation of state model for one of the basins in North America. It's Eagle Ford, very well known. And we had about 60 or 60 samples. And there were, I think, only 5% of the samples. And in unconventional, usually all the samples are separator samples. So when we did this Hoffman QC, we found that only 5% of the samples were actually showing equilibrium with this Hoffman plot. But as Curtis said, that what do you do with those samples is dependent on what's the objective of your sampling program and of all the PVT study that you have done. So the objective there was to develop the equation of state model. So what we did, we used all the samples that we had because we know that the composition, even though the separator samples, they were not in equilibrium, but we know that the lab has done a good job in determining the well stream composition that should be present in the PVT cell for the measurement of the PVT data, reservoir conditions like CCE, CVD, and DLE test. So we knew that well stream composition reported by the PVT lab, and we had all the PVT data measured on that well stream composition. So we used that data and with that known composition, we used the data for EOS model tuning, and we developed the EOS model for all the 60 plus samples. But as Curtis said, if the objective is for some reason is to get better K values at the separator conditions, or you want to know accurately what are the separator composition at separator condition, then you can do this equilibrium of the separator gas and separator oil at separator condition and find out the compositions of the equilibrium phases. And that's very similar to the ECM method that we are going to discuss after doing the exercises that we are going to do now. Yeah. So okay. So I guess we can start with the exercises. So the first exercise we are going to do is the flash calculation that we should have done in the morning. So it's pending now. So we go to the exercises and K values, flash calculation. Okay, so yesterday we did the k-value calculation with the standing correlation. So this is something we did yesterday. We calculated the k-values from the standing correlation at 100 degrees Fahrenheit and the separator pressure of 300 psi. So these are the standing k values, and then these are the fi values from the bi and tbi from the standing table. And then we calculated this log of KIP and then made this KPF plot. So plotting the log of KIP versus FI. So that's a straight line with the slope and intercept coming from the standing correlation. So now the next thing that we are going to do is to do the flash calculation. And the flash calculation, we know that if I just open the slide just to show what we went through in the morning. Yeah. So if you remember that when we were talking about the flash calculation, it's the Rice method. And what is the objective? The objective is to minimize this function and calculate the this vapor fraction. So that's something we will do here. So this is that function, Zi times Ki minus 1 over 1 plus Fv. So we will first calculate these values for each component. And then this will be the sum of all the values, and try to minimize this number by changing Fv. That will give us the vapor fraction from the flash calculation. And we know that for the flash calculation, we need the estimate of the k values, and the k values we are getting from the standing correlation. And that's something we discussed yesterday when we were discussing the k values, that the k values at low pressures, we have correlations that generally predict reasonable k values at those conditions, and standing correlation is one of those. So we will believe that the k values at these separator condition are reasonable from the standing correlation, and we are going to use those values for that purpose. Yeah, so let's just calculate this. And just before we start doing calculation, just to let you know that these separator conditions, again, separator pressure and temperature, these are from this gas condensate PVT report, because the gas condensate sample is actually a surface separator sample. So these are the separator conditions at the time of sampling for that particular sample. Okay, so let's do this together. So we have the Zi, so that's the Zi times Ki minus 1. So we have the Ki here minus 1 divided by 1 plus Fv. So Fv, that's this value that we are going to change when we will be trying to minimize the objective function using the solver in Excel. But like initially we have this 0.5 value, and then we just lock that, and then Ki minus 1, that's Ki minus 1. Okay, that should be good. So, and then we just drag this down. So yeah, so we have these values now calculated, and now we will try to minimize this function here using the solver, which we can find in this data menu. We have the solver, minimize this function by changing this y here, and then solve. Let's see what your okay, that's done. And so this is the vapor fraction that we have gotten, and it has minimized this value to.
And not the vapor pressure, but the vapor phase fraction.
Yeah, sorry, vapor phase fraction, or you can also say that's Fg, or you can represent it as Fv. So this is representing that if you have 1 mole of the well stream composition, then 0.8731 moles will end up into the vapor phase at that separator conditions, and then rest of 0.13 moles that will be of the liquid phase at the separator condition. Yeah. So now once we have that Fv value, then we can also calculate the composition of the equilibrium phases xi and yi. So xi, this is equation 1, I think, here in the. You can look at this. So that's this equation 1 here in the PowerPoint. So we calculate that the Zi divided by 1 plus Fv times Ki minus 1 yeah. So let's do this. Yeah, so that's the mole fractions of individual components in the liquid phase, and so that's about like 6.7% mole percent of methane in the separator oil, for example. And then yi now simply the Ki times xi. That's this here, and yeah. So, and we know that the sum of all the mole fraction has to be 1. So that's 1 here, and also this is also 1. And we have about 82.7 mole percent of methane, for example, in the separator gas. Okay, so that's the flash calculation. So what we studied in the flash calculation, that you need to provide a total composition, provide the pressure and temperature and some estimate of the K values, and that is gonna give you how many moles of the, like, first it tells you how if we have 2 phases, single phase or 2 phases, and we can see that we have 2 phases because Fv is somewhere between 0 and 1. So you have the vapor mole fraction somewhere between 0 and 1. So that is indicating that you have 2 phases. And then this also gives you the amount of the 2 phases. If we have 1 moles of the total well stream, then you have these many moles in the vapor phase, and the rest is in the liquid phase. And the third thing is that it is also giving you the composition of each phase, so xi and yi. Okay, so that's the flash calculation exercise. And now we go to the, so now what we can do, how we can use this flash calculation exercise for our for the samples that we have, like to do some kind of QC or that things like that. So because we now know that we have done the flash calculation and we have the xi and yi calculated from the flash calculation. So what we can do, we can compare these two compositions with the lab reported composition. Because for the gas condensate PVT report, at these separator conditions, lab has taken the PVT sample, the separator oil sample and the separator gas sample, and they have analyzed the PVT lab. So we know the xi and yi from the lab report, and we can compare those with these values that we have here. So that's, and we can also do this Hoffman QC that we will do on the next slide. So if we go to this next sheet, that's lab data QC, and here we can see this is something we have done now in the previous sheet. We calculate the vapor mole fraction and xi and yi at separator condition with the flash calculation. And now here we have the lab data. So the one thing that we can do first is that we have the separator oil density, we have the separator oil molecular weight, and we have the recombination GOR as CF per separator barrel. And we can calculate this vapor fraction at separator condition with the lab data and compare it with this flash calculation, for example. So I can just show you how where we got these values from the PVT report. If we just go to the PVT report, so that's the gas PVT report. Yeah. So, and also we need to open the formula sheet, for example. Where's the formula? Yeah. So if I just show you, yeah. So if you see this FG value, so FG, this is the same as FV, the vapor fraction of the gas fraction, and that can be calculated if we know the density of the oil. And here we are talking about the separator sample, so it has to be the density of the separator oil, and the molecular weight of the separator oil, and the GOR at separator condition. So if you know these values, we can calculate this FG value. That's the vapor fraction, the vapor mole fraction at separator condition. So now we will see where we can find in the PVT report these values. And again, these numbers, these have to be in the field units, so density in lb mass per cubic feet, and then GOR in SCF per separator barrel. So now if you go to the PVT report, yeah, so we need to find out where is the separator oil density at separator condition and the molecular weight of the separator oil and the recombination GOR. So first we see that this is the tables. This is table 7, which is showing the single stage flash of the separator oil. And this is it starts from the separator pressure, separator temperature, and here we have this separator oil density, the 0.753. This is the separator oil density at the separator condition, and that should be the same as we have in the Excel file. Yeah, so 0.753 gram per cc. That's the density given in the PVT report, and then we have the molecular weight of the separator oil. That's this number here, 138.16, and that should be here. And then the GOR 4922, we saw that yesterday. I think it was here. Yeah, so that's the GOR for the recombination the lab has used. So 4922. So if we want to calculate now the FG value, so yeah, so the formula now, go into the formula sheet and see the formula. That's 1 plus 2130 times the density, and the density is in gram per cc, so we have to convert it to lb mass per cubic feet by multiplying with 62.4, and then divided it by, we have the molecular weight of the separator oil, they are multiplied by the GOR of the separator oil, and then we just yeah, sorry. Yeah. and then you just do the power inverse. So that's 0.872. Okay, so yeah, so it's very close to what we have calculated from the splash calculation. Yeah. Okay, so and then these are the lab reported the lab reported separator oil and separator gas compositions taken from the PVT report, which are again here the separator oil composition on mole percent basis. So that's 7.79 in methane. So that's the same. This is 7.79, and then you have 82.8 methane content, for example, in the separator gas. So these are the lab reported compositions, xi and yi, and we can calculate the k values. So H2S, that's the first component. So there is no point in calculating k value because the mole fractions are 0. You can calculate it for other components. So these are now the calculated k values for the other components, and then we can compare these two columns with these two columns actually. So you see that the lab reported yi is 82.8 or 0.828 mole fraction, and the calculated yi is also about the same. There is a little bit difference in the xi, 6.7 versus 7.8. Somebody wants to say something? Okay. Yeah. So we said that we can do the QC, like this KPF plot or Hoffman QC, and for that we need this log of KIP times the pressure. Should be logged here. Yeah, and so we just drag this down, and then we have already plotted this standing log of KIP versus FI here. We have already plotted this, and now we are going to plot the lab reported log of KIP over the same FI values. So that's how it looks like if we plot the lab data. And you can see it's very consistent with the standing correlation, except for this heavier fraction. That's the C7 plus, which is off because of the reasons I discussed earlier. And this is this looks like a very good equilibrium check of the separator gas and separator oil samples on this plot here. Okay, and like here, when we plot the lab data, you should not expect the lab data to perfectly lie on this straight line, because there are some approximations or correlations being used when this relationship between log of KIP versus FI has to be a straight line. That's not 100% true. The data, like if it's a perfectly equilibrium data, then it will fall closely to the straight line, but not exactly on the straight line made between log of KIP versus FI here. And that's something Curtis is working on now, like how the method can be improved. And I guess Curtis, do you want to make any comments, or maybe it's too early?
Well, I think not really. I mean, there's the earlier question about what to do if the data don't seem to fall in line is the main, I think, struggle engineers have. And in using the method. If it doesn't seem to be consistent, what do we do? Should we just not use any of the data, or what should we do? So the work I'm doing is a little bit in relation to giving guidance on that. But I think I've already commented what I think could be done.
Yeah.
If it's not consistent. Generally speaking, the labs make this plot themselves anymore. And if there's a big deviation, I'm not quite sure what they will do themselves, whether they'll just report it as is, you would hope so, or whether they try to fix something to make it look more consistent. Probably varies from lab to lab what's done. Most of the things you see anymore do tend to correlate fairly well. And so.
I think we have a question.
Just.
Hello.
Yes.
Yeah. Can we go to the previous worksheet? Is the QC?
The QC this.
This worksheet. Yeah. So the one which we compared with the laboratory data, right? The C1 in the gas phase, say 82.8, right?
Yeah.
So is it from the recombined fluid, or is it in the separator flash combination?
This is the separator gas composition itself. This is lab YI.
Yeah, can we just check in the PDF file?
Yeah. So that's this. If you go to this report, so that's this separator gas composition. Okay. And then the other one is a separator oil composition.
Okay, and what is the previous page of this same?
Yeah, so that's the separator oil composition, and here, because that's something we will go through not the next, but the next topic. That's the compositions, like how PVT labs measure the compositions. And for the separator oil, they don't measure the composition directly, so they have to flash it first. That's ambient condition, get the flash oil and flash gas. These two compositions are measured directly, these two, and then they do this mathematical recombination to come up with the separator oil. So this separator oil composition that is shown here is the same, exactly same as shown here as well.
Okay, that the flash gas and oil in the previous page is not same as this one.
No, this flash gas and flash oil, they are coming from the separator oil, and here we have. So you get the separator oil here, and then you use this separator oil that we got previously and the separator gas that is analyzed separately, and you use both of them and use this recombination GOR to come up with the value stream composition. So that's your recombined field.
Okay, so this is going to be covered in detail later, right?
Yeah, that we will cover in detail in the. Yeah.
Okay.
Yeah, Hans?
Yes, just a comment to the Hoffman plot you have there, yes. The last one. It's not unnormal in the lab that you give something like that at the last point. It's not on the line.
Yeah,
it's a lot of reasons for that. It could be the laboratory, it could be the sampling. Normally what we are thinking about is that when you are just take a sample on the separator gas, and if you take it, you have to narrow the valves when you open it, and you get a Joule-Thomson effect. So you can get dropout of the heaviest end in your bottle. And if you not heat it up and mix it properly before you do the analysis, you can got something like that. But it can also be something in the lab. So it's quite not quite unnormal that we have something like that. I think it's good for our labs to do that, to take that check, and we do it ourselves. And okay, you can just do a small correction to get in the line, because mathematics is mathematics and lab is lab, and the lab is the real life, and you have a lot of things that can happen in the lab.
Yeah, that's very true. Curtis, you wanted to add a comment?
Yeah, no, I think it's good. I think it's a very good comment. It's the C7 plus. It's the it may not be in very large amounts in the separator gas. Could be part of the problem. Could be what's just been mentioned. Could be part of the problem. It's smaller amounts in the gas normally that's causing that uncertainty. And in addition to that, the calculation of Fi for C7 plus is only approximate. It's a correlation given by standing, which is not exact. So there's a number of reasons it might not follow on the trend.
Yeah, and that's why we don't give too much significance on that point. We have a lot of points that are supposed to fall on the straight line, and that should very well indicate whether the separator samples are in equilibrium or not. Yes, Hans?
No comment. No.
Yeah, thanks.
Okay.
Yeah, so I think we are finished with this exercise now, and there is the next exercise was to I forgot. It was we have this Watson characterization factor calculation, I guess. Yeah. So I think what we all do now, we just close this one. Also, you need this one now. Yeah. So regarding this Watson characterization factor, I guess we can all calculate the value, for example, for the oil sample and the gas condensate sample, and that will be also an interesting exercise. So first we can look at the PVT report from the gas condensate well. So that's the gas condensate PVT report, and always remember that when we are calculating the Watson characterization factor, and we want to know what is the value for our field, then we should always use the measured molecular weight and the density for the fluid system. And the molecular weight and density are only measured for the flashed oils, like the surface oils that you get from the single stage flash of the separator oil, or you get it from the single stage flash of the recombined sample. And since this is a separator recombined sample, so we go and see if we have a single stage flash of the separator oil. Yeah, so we have this single stage flash of the separator oil at standard condition, and you can see the comment here that this molecular weight in this table, the molecular weight is measured for the flashed oil and calculated for separator oil from material balance. So this is we're gonna discuss later how you can calculate from the material balance for the separator oil, but it's measured for the flash oil. So this is measured, and also the density is measured for the flash oil. So this is the footnote coming from this number here. So we know that the density and molecular weight are measured for the flashed oil. So we can use these two numbers, the molecular weight and the density, in the Watson characterization factor calculation. So yes, Gerardo?
Yeah, on the Watson characterization factor, does it, for different reasons, sometimes we flash at different temperatures, right? How will that change somehow the Watson?
Yeah. So if you want to be consistent, like if you have multiple samples from the field, and if you want to, and different samples have measured densities at different temperatures because of maybe the wax issue or something like that, then it's better that you correct all the densities at ambient condition, and there are correlations that you can use for the correction, the temperature correction, and use those corrected densities for the calculation of the Watson characterization factor, because the temperature may have a large impact on the density, the measured density value. Those have to be at the same pressure and temperature when you are calculating Watson characterization factor for the different samples.
Thank you.
Yeah, I think the answer to that is not clear. I'm not sure what it would be if you studied the effect of the flash temperature being 15 or 30 or 40 or 50. It might affect the aromatic isomers, in that range of temperature, which might move the Watson characterization factor coming from flashes at different temperatures. It might cause, but I think it's something, Bilal, we could look at later with one of the characterization that includes these aromatic isomers, C7 to C10, and see, maybe it does have an effect. I'm not aware, but it could.
Yeah, but so, what effect, Curtis, are you thinking about?
Well, if more of these like aromatics have a big effect on density, and not so much effect on the, also molecular weight, but and if at different temperatures, if the flash
liquid
can move those components more into the gas phase or less into the gas phase according to the temperature, then that could affect the quote unquote aromaticity of the resulting flashed oil. Whether it's a small effect or a big effect, I'm not really even sure, but if you go to high enough flash temperature, then you start moving the heavy components into the gas phase quite a bit more than you think.
Yeah.
So, we can look into it, maybe not during the week in the course, but come back to us maybe in a couple of weeks. We can take a look at that.
Yeah, that's great, because normally I know this idea of the wax, you increase the temperature, but then I'm always wondering on the other side of the equation, which is how much are you affecting the end result?
Yeah, and if the calculations show that you just, it's like marginal, then you can stop thinking about that.
Yeah.
Very good. Yeah, so I think here we can just calculate the Watson characterization factor. We already have an equation here. Marcus, can you do the job? Calculate the Watson characterization factor. Yeah, so we can just copy the equation. Curtis remembers it by heart, so that's amazing. But I don't remember it, so I just have to cheat.
What was that?
The Watson characterization factor equation, Curtis.
Oh yeah, it's burned into my brain, but you don't want that being there.
Yeah. And maybe when we will be going through this field-wide equation state model development, Curtis may share very interesting stories about how he remembered this equation and how he used that. I think it was for this field in UAE or Abu Dhabi, Curtis, right? Aromatic field.
Dubai, I call it the donut.
Donut.
Yeah, it was shaped kind of like a donut, but it was very aromatic oil, and they had not caught that in the EOS characterization. So yeah, it's an interesting story for another lunch when we're together.
Yeah. As condensate reports that we have a specific gravity, we have the molecular weight of the density is 79 and molecular weight 160.21. Okay, and then we calculate the Kw, which is equal to 4.5579 times the molecular weight, the 0.15178 times the density power minus 0.84573. So that's 12. And then I have to follow the Excel etiquette, otherwise I will be fired from the job. And then we have oil. And then same, we have the specific gravity, molecular weight, and Watson characterization factor. So if you go to that report now, So now this oil sample, this is a black oil PVT study, and this is a bottom hole sample. So we should not expect any separate oil samples, but we have the reservoir fluid that is flashed at standard conditions, because you collect the sample as a single phase. So you flash it at the reservoir at surface conditions, flash liquid, flash gas, and we have the measured molecular weight and density, which is very different than the gas condensate, and it should be, because the gas condensate has a lower molecular weight, the flashed oil, and flash oil density is also lower. So here the 0.845. So specific 5. The average molecular weight is 251.29. And then we just use the same equation. Thanks for Excel. Yeah. So you see that the Watson characterization factor is actually in if you look at the PowerPoint here, that's in naphthenic and close to the paraffinic range. And yeah, just as a comment, if we I don't know, yeah. So in the lab data, you see that we have these single carbon number. Like we have these components C6, C7, C8. These are the lump fractions. These are not pure components. And we have some estimates of the molecular weight and densities for these components. So C7 molecular weight of 96, 107, 121. And we also have some estimates of the densities. And these, like in most PVT reports, these generally come from Kac-Kruszabadi table. And if I just show you the PVT in this table in the monograph here, it's not open, so I just need to open that now. Monograph. That's chapter 5, I think table 5.1. Maybe I remember this thing only. So table 5.1. Yeah, so that's this is the experimental PVP analysis, the molecular weight and density, but then we have this table 5.2 where we have this analysis extended to this very heavy fraction 45, and here we have this molecular weight and the specific gravity from the Kac-Kruszabadi. So that's Kac-Kruszabadi generalized properties, molecular weight, average molecular weight, and densities for individual carbon numbers. And these are the numbers PVT labs generally use internally, and they're reported in the PVT report. And the data that was used to come up with these numbers, it was mainly paraffinic fluids. So with Watson characterization factors close to 11 or something. So you can see here that they have mentioned the Watson characterization factor for individual component, and you can see it's range from 11.96 to about 12 or something. So these are the fluid system that was used to come up with these numbers was paraffinic, and that's why these numbers are usually okay to use if you have paraffinic fluids. But if we have aromatic fluids, or if we have samples with very different Watson characterization factors representing more naphthenic or aromatic components, then and these numbers are not reasonable for the fluid, for those fluid systems. So that's why it's important to know what kind of fluid system we have, because these molecular weight densities, these are very important input to your equation of state model characterization. And we will see, like when we will go through the workflow of how we develop equation of state model, we will see how we come up with these numbers, the molecular weight and densities of individual components that are representative of the fluid system we have in the field. Yeah. So I think.
Yeah.
Yes.
Sorry, but normally the distillation is not something that we do seldom on the first exploration well, right? Something that we do after.
Yeah.
What will trigger, on your view, to do a distillation experiment, given the implications that you're referring to?
Yeah, that's a very good question, and yeah, that's always a challenge when you're developing question of state models that like TBP distillation data. Like I don't know how many people here are aware of it, but we will go through it in more detail when we will go through the compositions and lab PVT measurements. But TBP data is like it's kind of an ideal data that we would like to have to characterize the fluid, so that like to come up with this gravity molecular weight correlation. And as you said, that if you have an exploratory well and you haven't done those measurements, then you have only very limited data on this. For example, on this plot, you may have just 1 or 2 samples to come up with what's a characterization factor value, and then you are just assuming that this correlation is working all fine on all those on these ranges of molecular weight that you don't know, like generally, as I said, like we have this cards for the body or data measured, for example, for paraffinic fluids, and we have different correlations. And like if we don't have data, we generally just have to live with that. But like if you have very aromatic fluids, I don't know that there is any good measured data, like for example, cards for the body, for example, where we have this the molecular weight and density measured on a wide span of the molecular weights of the components. So in that case, one option is just to go with the correlation. Like for example, Watson characterization factor, if you have calculated for one sample 11, for example, you just assume that it works fine for the entire range, or you go for TBP measurement, for example. Yes, Curtis?
Yeah, I mean, in general, in a field that's going to, you request as early as possible for a single TBP analysis of one sample. It should be, I think it just should be a recommendation we always make for a given field. So that may come though later because you need larger samples, you need stock tank samples and things. So you may not get it early, and then you have to make do with what you have. The things that you typically have today that help building this relationship is you have the 7, 8, and 9 single carbon numbers with isomers. So you can actually build the average properties of C7, C8, C9. And those three should hopefully fall on the trend of whatever correlation you build. And then you have all of these flashed oils, hopefully with some valid, accurate measurements of average molecular weight and average gravity, right, with compositional distributions. So whatever correlation you've built, you want it to calculate those average flashed oil molecular weights, average flashed oil specific gravities from the reported compositions with that correlation. So you, so you have indirect information about that single carbon number correlation through the averages. And if you have enough samples with enough variation, then that's good data. This is just as an example here from Ecofisk fields. You know the average correlation. So what the single carbon number correlation should look like to give you that average correlation for, I think the one is Albichel, the other is, I think, West Ecofisk. It's a constraint on developing the correlation. So getting the average right for all the samples you have of flashed oils, honoring the C7, 8, 9 based on isomers, that's a big help to getting you to do. I mean, we use that approach without TBP data in many of our studies and feel comfortable with the final gravity molecular weight relationship we built. So you can do that. I think today it's easier because we get the 7, 8, 9 isomers and kind of anchor that correlation through those data.
Okay.
And, yeah, so you can do it, but eventually you'd like to get this TBP data for one per field, we feel like.
Yeah. Thank you.
Very good.
Okay, so what we'll do now is to cover ECM or equilibrium contact mixing as a topic before we're going to go into different PVT laboratory experiments. After that, I think Bilal will go back to taking over that part, but I'll try to cover this, and this is actually a very, it's kind of like a small passion of mine, a personal passion. This ECM equilibrium contact mixing or the methods associated with that. We will attach a go-to paper for this from '94, I think, written by Øyvind Fevang, which is now the chief engineer in Equinor, and Curtis Witzner with us. It goes through essentially all the different cases or scenarios where you can apply equilibrium contact mixing, and a little bit in different ways depending on what reservoir you're dealing with and fluid type. But before we go into the method as such, it's important to just answer the question. We're talking about ECM, but why and in which cases would that be relevant? So I'll just try to explain that real quick now with a bad drawing. So just imagine and this happens a lot when I talk to people in the industry where you have a well, and this is just here we're going to plot GOR, so the producing GOR versus time. So we used large RP for this. Let's assume it's an oil. We can say that the initial, the solution GOR of this oil is this line right here. We're starting to produce at some constant GOR before we get some kind of solution to gas drive effect, and the GOR goes up with time. And let's say we didn't do any fluid sampling early, or we lost the data. It can be an old field, and the only samples we have, and this is very, very common in, for instance, unconventional wells and old fields, and also a few new fields with limited budgets where they want to do sampling later in time and they want to reconstruct an in situ representative fluid sample. What options do you actually have for that? So let's just say we came in at this time right here, T star, and we wanted to do sampling at this point right here. And we would like to have a methodology to, computationally or in the lab for that matter, to reconstruct at least our best estimate of the in situ reservoir fluid composition. So the reservoir fluid composition that's represented by this RSI. One simple option, which is what most PVT laboratories would do by default, at least if they don't know about the ECM method, is that they would take the separator oil and the separator gas, sampled at this point in time, but instead of recombining at the producing GOR, they would recombine these at the initial producing GOR, so that was close to RSI.
Separator gas.
Oh, yeah, separator gas. Sorry. And this is, I guess, not recommended, and the results from doing this can be actually very, very wrong. We have some examples of that too. Versus doing what is and should be done, which is the method that we'll now discuss, which is ECM. So if you like when you think about ECM, what you should think about is a way to reconstruct an in situ representative fluid sample if you haven't been able to sample early, for instance. It is a pragmatic way as such, because you can do it both in the laboratory, and you can also do it computationally with an equation of state model. And even I think also for some corner cases of like gas condensate reservoirs with liquid dropout and whatnot, you have to use a computational model, so an equation of state to do this. Okay. So before we move forward, any questions to that? Just remember that that's why we're going to talk about this, and without going into all the details of all the different cases, we'll try to focus on one particular case. I believe an oil, an initially undersaturated oil case, but the general ideas and what I'm trying to convey with a few animations that is actually made by Marcus here on the side is the key points of why it is important to do it like this and not just recombining the producing or the separator oil and gas at the initial producing GOR, and why that in some cases can be very different. So first, there's a few claims here. Some of them might be a little bit debatable, and at least when we show it, but it's to initiate some discussion. So there's here I come with three claims essentially, and I think we talked about that earlier today as well. That in some cases it might be actually impossible to collect in situ representative samples. That's one claim, and the other claim is that it's actually not important to sample the perfect in situ representative sample, which we defined earlier. We'll get back to why. And the third claim is that we can actually use samples which are not in situ representative, but the reservoir representative, to estimate original in situ fluids using the ECM procedures. And that's what we're going to talk about today. And it's actually an old technology. I think originally, and here Curtis needs to arrest me if I'm wrong, but I think it originally was a couple of Danish people that presented their procedure, and then I think Øyvind and Curtis looked at it for all the fluid systems just after. Wouldn't that be about correct, Curtis?
Yeah, Jan Efsted's paper was basically specifically for gas condensates. Yeah. And it was a computational method. This was actually a method that we first looked at for the troll field, and to get good compositions of very lean gas condensate. So I think there's some differences. They were done independently, though, I know. But yeah, it's not exactly the.
Exactly. Yeah. Okay. Very good. So the first claim, it may be impossible to collect in situ representative fluid samples, and that's true in the cases where you, for instance, are producing with very high drawdowns or very rapid declining bottomal pressures, which is the case in low permeability reservoirs, for instance. Or the cases where you're producing from something that's initially slightly undersaturated or actually saturated in situ. So that's just two facts where actually what you produce at surface just short time after you put the well online, and potentially when you would like to sample, which is not, that's sometimes also a subject to logistical constraints as well. That they're essentially not aligned. So what you produce is not in situ representative, but they're most likely reservoir representative if it's not something very highly contaminated that you're producing back, or that you've injected. For instance, in some unconventional wells, you actually use nitrogen to inject when you complete the well and you produce back a stream full of nitrogen that's not there in situ. So some corner cases like that. The second claim is that it's not important to sample in situ representative samples. And the reason for that is that a PVT laboratory report is never used directly in decision-making analysis, but mainly there to create a PVT model. And when you create the PVT model, what you actually care about is not what's in the reservoir. It's not necessarily what's at surface. You want to capture what is actually happening within the PVT cell. So for the compositions that you input into the PVT cell, as long as they're reservoir representative of your reservoir, is what you in general would like to locate with the model. And then after that, you then essentially have, for instance, if you have an EOS model, you then have a model that can take in a composition, a temperature, and a pressure. And there's then the engineer's job through a process, for instance, like ECM, to find and input the right amounts of different components into the model to initialize the reservoir, and that's what we call fluid initialization of a reservoir model. And for all practical purposes, and we'll already talked about that in relationship with fluid sampling, but that's mainly to determine a spatial fluid variation. That's where, for instance, these MDT tools are very helpful, where you actually get spatial, exact compositional points in space. And in some cases, it depends on the complexity of the reservoir, where you are in the world, the amount of money you have available, etc. It's sometimes also common to assume a constant in situ fluid composition in the well box. But that's different from a very complex reservoir to a more simple system. Okay, so what I'm saying here is that when you do the laboratory report, the main objective when you're doing the lab analysis is to create very accurate measurements of the fluid in the PVT cell, and then we worry about whether that's in situ representative or not later. The third claim is that samples which are not in situ representative can be used to estimate the original in situ fluid using the ECM methods or procedures. And then the question is, okay, what is actually the equilibrium contact mixing methods? So here we have two references on that, the Pevang and Whitson paper and the Refstrup and Olsen paper from 94. We'll make sure to attach some reading material on that. But what it attempts to do is to use available samples to reconstruct the compositional path that the reservoir fluids are subject to during primary depletion. And we're going to discuss what are we actually talking about when we're talking about the compositional path. But it was introduced in conventional reservoirs in the 1990s, and it's not a absolutely perfect method. For some cases, it actually is, but it results in very, very good estimates of in situ reservoir fluids. It's simple and pragmatic. You can do it with the readily available tools, and in most cases, it's the best that can be done with the available data, and definitely better than the alternative, which is simply just to recombine the separator samples at the initial producing GOR. I promised to just briefly mention what we talk about when we talk about path, the compositional path, and what's important to remember there, which we've iterated a few times also yesterday when it comes to black oil table, that the surface process actually matters a lot, is that PVT is actually path dependent. So you'll calculate different PVT properties, whether you go through a one-stage process, a two-stage process, and a three-stage process, for instance, a separator process, where all these is what I at least call different paths. And also for a single setup like this will be a different final result if your first stage separator conditions in the one case is very high pressure versus a very low pressure, and that will impact. In general, say that PVT is path dependent. And here comes a short recap from university, at least the folks that have been doing like process engineering courses and maybe courses with Curtis or at other petroleum engineering departments. Is that the typical exercise you get is that you know the total fluid composition that's going into a surface process. This is a 3-stage process, and the 101 mistake in this case is if you only take the final gas and oil compositions and directly recombine to try to get this total well stream composition right here. And we'll talk more about this recombination, I guess, equation right here when we're going to talk about composition. But this is essentially not what you like to do. And what you learn about in university is that you should follow the compositional path over each separator. So you first have to recombine these two guys to get the composition that went into this separator, and then you get this guy right here, and then you need to use this composition and recombine over this separator right here to get this guy, and then you use this guy and this guy to get the total well stream composition. And this is the equation that you should use. And that's just to demonstrate it. It's one way to I guess visually think about why PVT is path dependent, and this is just at surface. And the ECM method tries to do something similar, where kind of the reservoir can be viewed as almost like as a stage in this separation process. So we need to ask ourselves, okay, now we talked about a surface process here, but what we are dealing with is reservoir fluids. So we need to ask ourselves what is the compositional path that the reservoir's fluids are subject to during primary depletion. And here, I think at this point, it can be nice to just mention that in conventional reservoirs, the producing GOR, so that's the RP, is a strong function of the average reservoir pressure. And in unconventional reservoirs, for the Wintershall guys, that will be down in Vaca Muerta, the same with the Equinor in Vaca Muerta and Bakken, it is a function of the flowing bottom hole pressure. So it's a difference there. And we're going to talk about conventional reservoirs right here. But for simplicity, just if you're talking about a shale reservoir, you just change bottom hole pressure with average pressure. So we're going to answer what is the compositional path that these reservoir fluids are subject to during primary depletion. So if you look at the well, this is a gas condensate well. That's why it's very common to plot CGR when we talk about a gas condensate well, and also here out of the average reservoir pressure. It looks a little bit dramatic, this reservoir pressure, average reservoir pressure, but it's to convey a point. Here's the dew point. And we're going to look at what happens with the CGR above the dew point. Well, the CGR, the composition is constant. This is what we talked about yesterday. We see that the saturation of gas close to the wellbore here is 100% gas. Then when we're dropping below the saturation pressure, we build up condensate saturation. The CGR is dropping down, and we're essentially saying, okay, if we wanted to do sampling at this point, what should we then do to find the initial gas composition in this case? And so this is the compositional path that these fluids are subject to during primary depletion. So now we just have an example for initially undersaturated reservoir oil. And the method is very simple, but it involves probably only one, at least from a high level perspective, direct recombination. So the first thing you do is to recombine the separated samples at the producing GOR. Well, the alternative was to do recombine these at the initial producing GOR. Then you equilibrate this mixture at the average reservoir pressure at the time of sampling. So that's a data point that you need to either estimate or measure with a well test. And then at this at these conditions, you'll then have you'll have a equilibrium gas and equilibrium oil that you mix in stages. So you first remove this gas right here, and you keep the oil I guess alone in the PVT cell, and you inject the equilibrium gas in stages until the solution or the solution GOR of what's in this PVT cell is equal to the initial producing GOR. Or if you actually know the bubble point, the initial bubble point, you can also use that as information. It's two sides of the same story. And this results in a mixture that's a very, very good approximation of in situ reservoir fluids. Yeah, and this is just talking about this case. So again, this paper right here, Accurate in situ compositions in petroleum reservoirs, is the go-to paper on this technology. Again, by Øyvind Fevang in Equinor there and Curtis. And this is just I guess a snippet from the discussion on depleted solution gas drive oil reservoirs. So here we can see that the produced well stream sample is prepared by recombining separated samples using the test GOR. The recombined mixture is brought to equilibrium at the current average reservoir pressure and temperature. All of the equilibrium gas is removed at constant pressure to another container. The equilibrium oil remains in the PVT cell. So you see that this is stuff you could either simulate with an equation of state, or you can actually do in the laboratory. The equilibrium gas is injected incrementally back into the PVT cell containing equilibrium oil, and after each injection, the bubble point is measured. When the bubble point reaches the original reservoir bubble point, the mixture can be considered a very good approximation of. And here we're using bubble point, but in cases where you don't know the bubble point, but you know the initial GOR, you use that instead as a constraint. And it's two sides of the same story. Very good. So I'll just show these now, and I'll just emphasize that Marcus on the side here has made all the fancy animations. So we have to give him credit for that. Hopefully it makes sense. So this is the volumes of oil and gas that we've or some part of the volume of oil and gas that we've sampled during the well test. We just recombine that the producing GOR or the test GOR, depending on the test GOR, hopefully is the producing GOR that day. Then you equilibrate that at the average reservoir pressure. So that's what we're trying to convey with this drawing right here, or animation. And then you remove the equilibrium gas. And then in different stages, you then introduce the equilibrium gas until the RS is equal to the initial RPI. So that's the initial producing GOR. Or you can use the bubble point constraint instead. And the resulting fluid mixture approximates the in situ reservoir fluid with a very, very high degree of accuracy, and it will also be very different than the alternative. And that's what's been verified in this paper. The rough paper talked about a special case, and I think also other papers since that. And for those of you who are interested in this technology, the different methods for your particular reservoir you can read upon in that paper, and is very well explained, I think, for saturated reservoirs, gas condensate reservoirs, etc. Okay, so the question is then, as you all probably talked about earlier today, what is actually then a non-representative fluid sample? And I hope you've spent a little bit of time to understand the difference between in situ and representative fluid samples, or reservoir representative fluid samples. For all practical purposes, at least in this world, then a non-representative fluid samples would essentially mean a fluid sample that is contaminated with either a mud, inject some kind of molecule that you are actually producing back for instance, as a nitrogen or something else. Very good. Any questions on this topic? Curtis, anything to add?
Yeah, maybe the one case that's not so unusual is a well that early on is coning. You know, what we just kind of went through was more undersaturated oil that develops a gas oil ratio when it goes below the bubble point. But if you have a gas cap oil, and let's say you're testing the well and your perforations are close enough to the GOC that during the test you start getting gas coning in from the gas cap. That case is also addressed in the paper, and it's actually shown that that particular situation is really ideal. It's a great way to get a very good estimate of the initial gas oil contact fluids, gas and oil. So that's just one extra case that I don't think you mentioned that per se.
Yeah. Wasn't that also related to a question we had yesterday about, didn't we have a GOC question yesterday?
Yeah. If you only had sampling for the 1 phase, wasn't that the question?
Yeah, there was a question from Gerardo. I can't remember exactly the wording, but about that you have a gas condensate reservoir that has an oil rim, an underlying oil rim. And can you repeat that question, Gerardo, if you're with us?
Yeah. No, it was related to we see that in some of the fields we have a large gas condensate, and we have an oil leg underneath, and sometimes they don't seem to be chemically in equilibrium when you take samples in the oil leg and in the condensate leg. They are a bit off when you measure the individual properties, and it's hard to combine them to explain why they are together in the same oil column.
Yeah. So you know, if it's known to be a initially saturated reservoir, then this method would give you the compositions initially at the original gas oil contact, so that you may not have those samples from, you know, you may have samples deeper and you may have samples shallower, and there can be a variation with depth away from the gas oil contact, right? So the samples away from the gas oil contact becoming more undersaturated in the oil and maybe still near saturated in the gas, those samples away from the gas oil contact won't be equilibrium samples.
No. Okay.
But if you use this method, you take the deepest oil and the shallowest gas samples that you have, and you construct that into a mixture and equilibrate at the initial GOC, that will at least tell you what are the compositions at the initial GOC. And that becomes important data in the EOS tuning and also the fluid initialization both. So you use these samples away from the GOC that are not in equilibrium with each other to create that equilibrium GOC gas and oil. And that's real useful data for tuning the EOS and initializing the reservoir fluids spatially.
Yeah. Okay.
Gerardo, when you're talking about these examples that you have a gas condensate and an oil rim, so are you talking about like samples collected near the GOC and you found that those were not in equilibrium? Or do you have such samples which are collected near the GOC in a field?
Yeah, it's an example that comes to my mind. It's Equinor is operator, and we are partners in that. But I don't know if I should mention it in here. Yeah.
Okay. Yeah, maybe take it.
Okay. Okay. Very good. And maybe we can cover the difference between a saturated and undersaturated GOC.
Yeah, we'll
on
talk about
Friday.
Friday.
Yeah.